And now we have the last talk by Terrace. Thank you, Terrace.
Thank you, Don. Yeah, so here I put some summary of what we discussed yesterday. So we have a vector space, k-dimensional vector space, and we have a spanning vector configuration in the dual space. And out of that, we construct what's called the exponential action of the small vector space on a large vector space, which is defined by this coordinate-wise multiplication by these exponents, where you have those vectors in your configuration paired with the element in your acting group. So now there is a concept of this Gale duality, where you have a pair of dual short exact sequences. Here the map gamma takes the basis vector to the ice vector in your configuration, and W is a kernel of this surjective map. Then you dualize. And similarly, this ice basis vector is mapped to some vector in the dual of this kernel. And in this way, you obtain a configuration of M vectors in this vector space of complementary dimension. And this is a Gale duality between those two vector configurations. And now, in terms of this Gale duality, we had this criterion for the exponential action restricted to an open subset defined by a simplicial complex K to be free and proper. So once you have a simplicial complex and you have a pair of Gale dual configurations, then the following conditions are equivalent. The first is that restricted action, the action of V on this open subset, is free and proper. Secondly, that this data, simplicial complex, together with a vector from your A configuration, form a simplicial fan. So this collection of cones spanned by subsets in your configuration corresponding to simplicial simplices in your simplicial complex form a simplicial fan. Or in other words, this relint means relative interior, so that's interior in the ambient affine space. So if you look at the relative interior of cones, different cones in your fan, then they are pairwise not overlapping. And then there is a Gale dual condition that if you look at the Gale dual cones, you look at the complementary configuration and look at the cone of the dual configuration, then it's the opposite. The relative interiors overlap. Let's illustrate this by an example. So you have this fan, which is familiar to people doing toric geometry. It's a fan of the two-dimensional Hirzebruch surface. So it's A1, A2, A3, and A4. So this is a complete two-dimensional fan, right? So we have 4 vectors and 4 two-dimensional cones, 4 one-dimensional cones, and 1 zero-dimensional cone. So the A configuration, I write it as a matrix with columns. Yeah, so that's 1, 0 for A1, 0, 1 for A2, then -1, 0 for A3, and finally -1, -1 for A4. So that's A1, A2, A3, and A4. And now you want to produce the Gale dual configuration. How you do that? Recall that you need to, so there are 4 vectors in two-dimensional vector space. So there are 2 linear relations between them. And you need to pick 2 linearly independent linear relations between those 4 vectors. And well, For instance, you can take A1 plus A3 is 0, that's 1. A1 plus A0, this plus this is 0. And another one is A1 plus A2 plus A4 is 0. So there are 2. And then you write down the coefficients of that relation as a rows in your matrix. That's 1, 1, 0, 1, 0, and now 1, 1, 0, 1. And then the columns of this matrix is a Gale dual configuration. So on the picture, that would be, here you have, okay, here you have something like this. So here you have two coinciding vectors, gamma 2 equals gamma 4, and then gamma 1, and then gamma 3. And now, so this is a geometric information. And now you have a combinatorial information, the simplicial complex, which tells you which cones form your fan, right? So in this case, the simplicial complex is you just enumerate simplices which correspond to cones. So for instance, 1 and 2 is a cone, so you put 1, 2 here. So this is a simplex. Then you have 2, 3 is a cone, so you have 2, 3. Then you have 3, 4, and you have 1, 4. And then, of course, you need also to include one-dimensional cones, so like you have 1, 2, 3, 4, and also you need to include the empty set. So that's your simplicial complex. So the fan information, the fan data is this simplicial complex and this vector configuration. And the fan condition is that whenever you take cones, they do not overlap pairwise. And let's see how this translates by the Gale duality. So now, so for instance, 1, 2, you take the complementary, it's 3, 4, and so that that would be this positive O. Yes, okay, so let's say cone on A1 and A2 corresponds to cone on gamma 3 and gamma 4. That's complementary, right? And say cone on A2 and A3 corresponds to cone on gamma 1 and gamma 4. Okay, so if you look at that, then you see that actually not just those dual cones overlap pairwise, but they have the total intersection is non-empty, right? So this one is actually the intersection of all. This one is the intersection of all of the relative interiors. So it's actually, in this case, you have a stronger condition than just those Gale dual cones intersect pairwise, right? But the whole intersection of this one is non-empty. And this, in fact, tells you that not just you have a fan, but this fan is a normal fan of a polytope. Right? So you can draw a polytope, a trapezoid in this case, whose normal fan, whose normals are these vectors. And in 2 dimensions, that's a sort of exercise that every complete fan that you can draw in 2 dimensions comes from a polytope. So this condition that it's just not just their pairwise intersect, but their total intersection is non-empty. But starting from the dimension 3, you can see that from that Gale duality, how this condition is stronger, right? So that's the fan condition. So if the cones intersect pairwise, that doesn't guarantee that they have non-trivial intersection in total, right? And that's precisely the condition for the normal fan that puts us into the situation of symplectic toric manifold or projective toric varieties. Yeah, but I'm not sure that I'll have a have time to explain that in more details, but that's how it is. Okay, so now let's see how that relates to the main subject of our school, the toric topology and polyhedral product. So, okay, so you have now this group R, which is formed by those exponents. So you can think of this exponential action is an action of the real vector space, or you can instead look at this group. So that's the exponent, component-wise exponent of the kernel of the A map by the Gale duality. So you can also write it down as a set of exponents for X in the kernel of the A map. Okay. And then this is something more familiar in toric geometry. That's a real part of the algebraic torus in the quotient construction of toric varieties. So I'll write it down also in this way, using this Gale dual fan vectors, fan generators. So this is a subgroup in the real m-dimensional sort of multiplicative group of m tuples of reals. A real algebraic torus. And that theorem says that it acts on U of k freely and properly if and only if this data defines a simplicial fan. In R. And then, okay, so now once you're in a fan situation, you can look at the quotient, and that quotient is a good quotient. It's a manifold, right? It's a Hausdorff. It's a quotient by a proper action of a free and proper action of a Lie group. So it's a manifold. And so you can say that there is the following criterion of compactness for the quotient, which is also familiar in algebraic geometry, but here it has a purely topological meaning. So this quotient, or you can write, the quotient by V or the quotient by R, it's the same. So, is compact if and only if the fan is complete. So that the union of all cones is a whole space.
Mm-hmm. How is this manifold related to the toric variety?
Well, that's what I'm going to explain towards the end of this lecture. Yeah. So that's the first thing, right? So first, I'll tell you how it's related to polyhedral product, right? So now, once it's compact, then in this case, that's a continuation. There is a homeomorphism. The polyhedral product of D1 and S0, so which is also known as a real moment angle manifold. There is no better name for that. There is no angles here obviously, but still.
So the K is the combinatorics of this fan.
Yes. So they, oh, well,
K.
K. There's a K always mean the same thing here. Yeah. So it's a combinatorics of the fan. Yeah.
This fan.
A fan. So you start with an action and this set, right? And it tells you that the quotient is good if there is a fan here, right? If there is no fan, the quotient is not good, like we've seen yesterday with those hyperbolic actions. Yeah?
So is K is the dual of the polytope that you wrote there? In the
There is
picture?
no polytope in general, as I explained in this example.
Okay.
Right? In this case, there is a polytope, but usually those cones intersect pairwise, but there is no common intersection, so there is no polytope.
Is there any chance that we can get you to do the example here?
Yeah, I will do example. Hopefully, yeah. This is one of the examples. Yes. Oh yeah. Okay. Let's do a simple example, right? So, okay. So that what you actually do here, how you proved it. I'm not going to prove, just very basic idea. So that I'll give a very simple example. So you include this one into R. So this is your U of K. And so here you use just the factorial property of the polyhedral product. You include this is just a segment, right? So include the segment into R, include the 2 points. So this is just minus 1, 1, okay? And now then you each V orbit intersects. You prove that each V orbit intersects this RK, this thing, at a single point. So in that example that we drew yesterday, like you have this, so if you say K is just and you have this fan with two vectors A1, A2, which is 1, this is minus 1. So if the fan data is this one, then you have this concentric circles as an orbit space, but you can also realize it as a square. This square is if K is just those 2 points, then the real moment angle complex is this square formed of 2 segments. And you can see that this square intersects each orbit of the V action at a single point. But as you see, this one is not smooth. It has corners. But when you do it this way, you get a smooth structure on the quotient. So you like smoothen those angles. So it has a smooth structure coming from this quotient representation, all right? So, okay, so that's how you prove this. All right, so that's a real story. The story with real action. Now you can do 2 twists. You first can consider everything as acting on this complex space rather than a real space. And that gives you the complex moment angle manifold, the moment angle manifold instead of the real part. And also it gives you a complex structure on it. So that's, and secondly, if you combine the 2 things, then you can get the algebraic action coming in the quotient construction of toric varieties. So I'll go through these 2 other versions of this exponential action, and that will tell you how to put geometry onto a moment angle manifolds, how to represent it as a complex analytic manifold, and also how to produce toric varieties out of this construction. So let's say holomorphic exponential So now assume, so the idea is, okay, so I mean, we had this gadget, and we know that it's if K is a sphere triangulation, triangulated sphere, then it's a topological manifold. How to make it smooth? Let's tell you how to make it smooth, to write it down as a quotient. That only works in a case when K is not just a sphere triangulation, but it comes from a complete simplicial fan. But that's already quite a lot. That's much more than, say, boundaries of simplicial polytopes, for instance. Okay, so now you can put even more geometry by making everything holomorphic. So for that, we need to assume that the acting space is even dimensional. For those of you who are familiar with the combinatorial part of toric topology, you know that that's not really a big restriction, because you can always achieve that by adding ghost vertices to K. So, like, so here, everything is happening in m-dimensional space, and this K, you can, so if you have a fan data, that's now happening in n-dimensional space, right? So this fan is in, yeah, okay, it's here. This fan is in n-dimensional space, so you keep n unchanged, but by adding a ghost vertex, you can, this one is also m minus n. So like you increase m by 1 by adding one ghost vertex, and you keep n unchanged, and that makes it even. But if it's even dimensional, then you can put a complex structure into it. You can consider, you can put a complex structure, so that's a operator whose square is minus identity, and consider the corresponding complex vector space. Now the dual, the R dual, which is we denoted V star, it also has a complex structure as That's right. So you need to remove the hyperplane, the coordinate hyperplane corresponding to this new added. Yeah, so like adding a ghost vertex to K results in multiplying U of K with C star. Yeah. Yeah. Oh, sorry, with R star in this case. So far, yeah. So that's just a linear algebra. It has a conjugate complex structure defined by this formula. And then you have the dual vector space, also has with this complex structure, we denote it by V star with tilde. Okay. And that now this complex vector space is identified with the complex dual of this one, but there is a minus sign at some place, so that's like the map goes like this. Okay. So now you had this, now if you have the vector configuration in W star, then you can also consider it as a vector configuration in this complex space. This is the same set, it just has more structure. Right? But as a set of vectors, you can think of them as a complex vectors rather than real vectors. if you put, so like in a sense you like, there are many ways to put this complex structure, but that you think of that configuration as just a subset. So now they're in the complex space. And you continue assuming that the real span is a whole thing. And then you can define this holomorphic exponential action. Now you act by this complex space on m-dimensional complex space, again holomorphically. Now here you have the complex inner product of pairing and you multiply. So the two things are related by this commutative diagram. So you have here holomorphic action, and here you have the norm map, component-wise, coordinate-wise norm map. Here you have the identity times this norm map, and this is a real exponential action. And now, okay, now you can define, now you can repeat the whole setup in this holomorphic setting. So I'll just change something here in order to not write it again. So that's fairly easy. So now you look at the complex. So you see how it changes. Yeah. So now you look at the complex coordinate subspace arrangement, which is a complement in a complex space. So you throw away planes, coordinate planes corresponding to non-simpleces. So whenever you have a point in this U of k with some zero coordinates, then the zero set of this point is a simplex in k. Yes? No. So far there is no complexification. Yeah, the complexification will appear towards the end when we consider algebraic action. At the moment we put a complex structure on this vector space, right? We are not complexifying it. Complexifying like you add w plus w and then put a standard complex structure on this sum. But here we're doing something different, right? We will look at this real vector space and put some complex structure onto it. Or you can think, starting from the beginning, you act by a complex vector space and use a complex pairing here. That's just, we wrote all these things to relate this holomorphic setup to the real setup, right? But otherwise, you can just start with the action of a complex space on a complex space. Right, so then you have this complex coordinate subspace arrangement. Again, you have the pair of Gale dual configurations, and then you have the same, basically the same statement. Well, you need to prove it separately, but that you can reduce it to the real case using this. Well, that's not, of course, yeah. I didn't prove this one. I only illustrated it on a very simple example. And you need really to show that this fan condition translates into the properness condition. You have to do things here, yeah, to prove that. Okay, so. Now, again, yeah, and you can say that the quotient is compact if and only if the fan is complete and so on. So now, here, you have this one. Yes?
In that square over there, this question, you took the norms, so that you didn't just take the forgetful part, forgetting the complex structure, it could have ended up in 2 enough.
Well, that's identity is a forgetful functor, basically, yes.
The dimensions, I mean, it's a two-dimensional, but there are
Yes. So that's what I'm just erasing. As a complex vector space, it has half the dimension. So now we have H instead of that R. It's a holomorphic subgroup. Now this is a holomorphic subgroup in an algebraic torus. And you can check that it's actually a closed subgroup, a closed holomorphic, but not algebraic. Subgroup in this algebraic torus. Because there are exponents here. The exponents are holomorphic but not algebraic, yeah. Well, basically it is H, it's just isomorphic, there is no global stabilizer, so the action is free, well, so that H is just isomorphic to V. We'll see that if we have the spanning configuration, then there is no identification through this exponential taking exponents. So that's just the L-dimensional vector space included as a closed subgroup into the C star to the power M. Right? That already looks a bit weird, but we'll illustrate it on an example. And it acts on U of K holomorphically. So now if sigma is compact, is complete, then let's put it as a theorem. So if sigma is complete, then U of K modulo UC of K modulo this H is homeomorphic to the ZK, which is a complex moment angle manifold. That's you prove in essentially the same way, or you can use the doubling constructions that Tony mentioned to say that every complex moment angle manifold is a real moment angle manifold of some other simplicial complex. And do that.
Is it C to the L or C star to the L?
C to the L, that's important. It's C to the L. It's just the same, it's isomorphic. You just take V and exponentiate it coordinate-wise, like with these things. And it embeds. There are no gluing. I'll give an example shortly. Yeah. Homeomorphic, like this. Homeomorphic, yes. Each V orbit intersects ZK at a single point. But now, so what's important here, so ZK becomes a complex analytic manifold. Because now you have a holomorphic group action on a complex space, and that puts a complex analytic structure on this moment angle manifold, which has lots of consequences, right? So that gives you a very vast family of compact, two-connected, well, not generally two-connected, but like sometimes complex analytic manifolds, which are very far from being Kähler or projective. So that's all, basically all known examples, or at least all early known examples of families of non-Kähler complex manifolds, like Hopf surfaces, Calabi-Eckmann manifold, their deformations, they all fit into this framework. So that gives you a really large polygon for non-Kähler complex manifolds for testing. So okay, so let's do an example now. So again, we use this kind of, let's do it. So K, L is 1, right? So you have one-dimensional group, H. And that sits inside C star cross C star, which is U C of the empty set, as we know. The empty set considered a simplicial complex on two elements. So here you have K equals empty set on the set of two elements, right? So here you have somehow L is 2 times, L is 1 and M is 2 and N is 0, right? So you have zero-dimensional fan, but it's with two ghost vectors. So, okay, so now if you just look at a subgroup like this, so those gammas are just complex numbers. So this C is like R2 with a complex structure. And now, well, there is an exercise in complex analysis that that this group is closed if and only if either gamma 1 and gamma 2 are linearly independent over R. So this is our case, right? We assume that the R span is a whole space. They are linearly independent over R. Or their proportions, they are linearly dependent over Q. So in the intermediate case, that group will be not closed. It's like a dense winding of a torus or something like that. But it's in an algebraic version of that. Sorry, a holomorphic version of that. And in first case, so in the first case, of course, well, in the first case, you have C star cross C star over H. This is just, sorry, this is the same as, so this is isomorphic to C. If they are linearly independent over R, then this is just an embedding of C. So that's now like your V is C, right? So this is a one complex parameter V, and so this C, and it embeds into C cross times C cross as a closed subgroup. And the quotient, well, you know that it must be compact complex manifold of dimension 1. There is no choice. There is no much choice. So it's actually, if you think about this, you can cancel one of those C star by this C, and then there will be additional identification of the second factor. So if you do it properly, then you can actually identify it with C modulo the lattice generated by those two vectors. So this is a one-dimensional complex torus. Holomorphic, one-dimensional holomorphic torus. The elliptic curve. Well, in the second case, you just take, in the second case, when those two things are linearly independent over Q, that's not our case, but I just say that, okay, if they are linearly independent over Q, then this H is not an embedding, it has some gluing, right, over the lattice. So then it's just C star, non-compact. Okay, and more generally, let me write it here. More generally, you can look at the empty simplicial complex on M. Okay, maybe yeah, I'd better erase everything here. That's a continuation of that example. You can look at K as an empty simplicial complex on the whole set of M vectors, so that your A configuration is just 0. It consists of M zeros which is just a 0 vector space, and the Gale dual configuration gamma is a basis in V star, right? But then you have UC of empty set is C cross to the power M. Remember, that's a polyhedral product, right, of the empty simplicial complex. So that's just that second factor. And that K is C. That's your U of K modulo Rm, which is this one. So this is just the M torus, as you expect. But that's a real part. It's not really interesting, right? You just get an M torus. But holomorphic part is more interesting. Holomorphically, you're making a choice here. You choose a complex structure on this space, if M, provided that M is even dimensional. So if M is even dimensional, then you consider, you put a complex structure onto this, on this vector space, and then again you get C over. Now this becomes CL, the complex space of half the dimension, and now you act on by the CL on C star M. So this is precisely half of the dimension of this one, and you get a complex torus, a complex manifold, depending on. So well, if you think of that carefully, then you can identify it with a conjugate of this space modulo the lattice generated by these vectors, where gamma 1, G1, gamma n is dual, a conjugate to gamma 1 through gamma n. So R conjugate. So these things must sit in V, and those gammas were in V star. So you take the dual, R conjugate basis, apply the complex structure, and that gives you the lattice. So that's similar to this kind of one-dimensional situation. And so this is a holomorphic L torus. So in this way, by varying this complex structure, you can get any holomorphic torus. Any complex, so this is a torus, and you can put any complex structure on that from using this construction. So that, and you know, some of those tori are algebraic, but some others are not. So I mean, the one-dimensional one is always an elliptic curve. It's always algebraic, but those holomorphic tori, there are many non-algebraic tori among them, but all of them are examples of these complex analytic structures on moment angle manifold. Okay, now, the last bit I wanted to talk about is to link that back to the quotient construction of toric varieties, which I just started from. So, okay, now I'll leave this example here. No, probably right here. So that now you look at the algebraic actions. So now, up to this point, there were no rationality, there are no lattices, apart from this lattice defining the torus, but no lattices in our spaces. And all our fans, we considered simplicial fans, we considered complete fans, but we didn't put any rationality conditions on those fans. Now, if you want to do it algebraically, you want to consider rational configurations. Because toric geometry is convex geometry of rational fans, right? So we say that this configuration is rational if its z span, z of gamma, is discrete, a lattice. So there are many vectors here, more than the dimension, right? So if you look at the integer combination of them, then generally they will accumulate. There will be the group generated by the linear combination will be not discrete. But if it is discrete, then we say that this configuration is rational. So that basically says that if you put a basis in this, then you can somehow choose a basis in this ambient vector space so that those vectors have rational coordinates. But that's an invariant way of saying that. And because the R span is a whole space, it's a full rank lattice. So this is a lattice which you use to produce a toric variety, right? So the toric geometry starts from a lattice, and then you get a torus and eventually a fan. So now, that's the lattice in this dual space. You can look at the dual lattice, which is L. So that's just gamma star inverse. This is gamma star of Zm. So you can write it as a set of vectors in V which pair with gamma integrally. Now you can, once you have a lattice, you can define an algebraic torus by tensoring with C cross. Or you can say that now that the complexification comes into picture, so you can identify this complex torus coming from this lattice L as a quotient of the complexified vector space by 2PL. So this is a complexification. And of course, you can decompose this torus as a product of V and the compact torus, where TV is a compact torus. It's a product, tensor product of the same lattice with S1. That's a compact torus. Okay. Yeah, maybe. Okay. Yeah. Now you have this injective homomorphism, right? You have this that C, that algebraic torus embeds into the big torus, big algebraic torus via so you have a map from V to Rm. Now everything is rational. So there is a lattice here it's called L, and that lattice L here maps to ZL. And then you look at the map of algebraic tori corresponding to this map of lattices, tendering with C cross. Okay. And so now this is a algebraic map. So you can define this algebraic subgroup HC as an image. So this algebraic torus embeds into this big algebraic torus. So you can write it differently like we did with real or holomorphic counterparts. Either this way, that's, or the exponential of the kernel of the, now this is a kernel of the complexified map. Again, you can complexify that pair of Gale dual diagrams. So, all right. So if you do it with an arbitrary vector configuration, then you get something which is not closed. But since we started with a rational configuration, it is closed and even algebraic. If gamma or A is rational, because then we can write it down as follows, like we did with the real and holomorphic subgroups, as a product of Ti AI W equals 1. That's the kernel of this map. So using that Gale dual sequence where W is in the Gale dual lattice. So there is a Gale dual lattice to L which sits inside this space. So that's L goes to that M and that goes to this M star. So this is a dual lattice. And this is the lattice where the toric geometry starts from. That's a lattice of one parameter subgroups of the algebraic torus acting on a toric variety. So now these are algebraic equations, like, because here the exponents are integers. So these are algebraic equations, and this is an algebraic closed algebraic subgroup, which is isomorphic to an algebraic torus of dimension k. And then again, you have the theorem, which is the third manifestation of that fan condition. But now if you look at the algebraic action, then this is precisely the statement from toric geometry. So this is proper. Well, not quite. I mean, it's a bit stronger, but still. Yeah, if and only if the data defines a fan irrational simplicial fan sigma. In which case, it's not, if in the real and holomorphic case it was actually free, but this times you have also that torus factor here, the compact torus factor, so it may have finite stabilizers. It's almost free. So the quotient is a algebraic, is an orbifold, algebraic orbifold, which is known as a toric variety. So this one is the toric variety corresponding to sigma. This is a quotient construction of toric variety. due to battery of Kochs and others. I should put all the symplectic geometers here as well, like Atiagi, Guillaume and Sternberg and Carvan and Oden. They were all prerequisites for this quotient construction of toric varieties. Okay, so, well, that was earlier. That was like another one. The patching from fan is like original one, but then it's like at the beginning, end of 80s, that thing appeared as an alternative way of writing them down. Okay, so I'll finish with a diagram which relates all those. Yeah, I'll probably leave this example, which it will, as it will appear in. Yes, so you have this UC of K, which is an open subset. So it's the same as a polyhedral product CC cross to the power K, and it sits as an open subset in CM, as a quasi-affine variety. Now you have this holomorphic exponential action. You take quotient by H, which is isomorphic to CL, to get a complex analytic moment angle manifold. The complex moment angle manifold by taking the quotient by this holomorphic torus section. That always exists, regardless of whether your configuration is rational or not. But if you are in the rational situation, then you can take a bigger quotient by the complexification of this thing. So remember that in this group is algebraic only if it is you start with a rational configuration. And in this case, this one is isomorphic to C star to the power L. Oh, sorry, to the power 2L. It's twice dimensional. Yeah, so this K here is 2L, right? And now the quotient is a toric variety. Okay. And now, of course, this is like the halfway through. So you can look at this map, which is the quotient of HC. So this one is a complexification of this Lie group. And so the quotient is just this one. It's a holomorphic torus. So you have CL sitting inside C cross to the power 2L, like here. So this is just a slightly unusual way to write down a holomorphic torus. Instead of writing as a quotient of CL by a lattice, by a full rank lattice, we write it as a quotient of C star to the power 2L by CL. So this is a holomorphic torus. So that's this one is a holomorphic torus bundle. And that's like the standard vibration from the Davis-Januszkiewicz construction of the moment angle manifold to the toric variety, where the fiber is at m-n dimensional torus, but now you put the holomorphic structure on all those pieces. And it becomes a holomorphic torus bundle, right? So if, in general, it's just this is an orbifold, so you have to be a bit more careful. It's what's called the Seifert bundle. So the fibers are holomorphic tori. And it's called sometimes generalized Calabi-Eckmann fibration. Well, yeah, I think maybe I'll just use 2 more minutes to illustrate this on a very simple example why it's called Calabi-Eckmann. Because one of the early example of a non-Kähler complex manifold was a Calabi-Eckmann manifold. So if you start with a product of 2 Hopf bundles, that's a product of two Hopf bundles over the complex projective space. The fiber is S1 cross S1. So now Calabi-Eckmann and Eckmann in 50s observed that you can put a complex structure on each fiber with the same parameter. So you make this torus an algebraic or a holomorphic torus with the same lattice parameter along all the fibers, so that the whole thing becomes a holomorphic fiber bundle. The map becomes holomorphic. So that one is a is called Calabi-Eckmann manifold. So that's a product of odd-dimensional spheres with a particular complex analytic structure coming from this fiber bundle. And this one is two connected, right? So it doesn't have second cohomology. So it cannot, there is no way it can support a symplectic form, a Keller form, it can be projective, nothing, right? Because there is not second cohomology to support all these things. That was one of the, where this non-Keller complex geometry started. And now this is a just generalization of this one, right? As you see, this is a toric variety, this is a holomorphic one torus as we described, and this is a moment angle manifold. But now there is something interesting happening here. I'll finish with this. So this thing corresponds to a rational configuration. So now if we start with this fan, for instance, this is a fan for the product of complex of product of complex projective lines. But then you can start deforming it, right? So that it's no longer rational. So you can move that tray to this one. Well, of course, it loses rationality in the process. So that means that these fibers here, the tori, they open. They are no longer closed subgroups. So you lose this fibration. So instead, you have like a foliation with a non-compact fibers. And that foliation deforms to another rational point where you have this Hirzebruch surface, right? So you have this complex analytic structure on moment angle manifold. They, as a rational point, they have all toric varieties. So that's why they're considered as a model for the irrational deformations of toric varieties. So that's moment angle manifolds together with a section of this group, which is closed only when you are in rational point, but in general, it's open, it's not closed, like a dense winding. So that foliation is a model for the non-rational, irrational toric varieties. Yeah, so that's, there is lots of things to study here. Okay, so I'll stop here. Thank you.